This question is from GATE 2015 Mechanical Engineering paper, set 2, question number 33. A cantilever beam with square cross section of 6 mm side is subjected to a load of 2 kN normal to the top surface as shown in the figure. The Young's modulus of elasticity of the material of the beam is 210 gigapascal. Magnitude of slope in radian at Q 20 mm from the fixed end is dash. Now we need to find the slope at point Q, and for that we will use slope deflection method because that is the easiest one to use here. Easiest and the shortest one to use here. Let's start by writing the given information. Modulus of elasticity E is given to be 210 gigapascal. So for using in the problem, we will use it in Newton per meter square. So 210 into 10 to the power 9 Newton per meter square. That is pascals. Side of the square cross section A is given to be 6 mm or 6 millimeters. Hence we can calculate its area moment of inertia I as a to the power 4 by 12. So we'll use the values of E and I later. Now let's take point P as the origin. So at point P, distance x will be equal to 0, and then towards the fixed end, x is going to increase. We can say that at O, x is equal to 100 mm. Let that be L, that is 100 mm. And at Q, this value of x is 80 mm. Because this is 20 mm, so from P, if we consider the distance, it is 80 mm. For finding the slope at point Q, easiest method is to use double integration method. It will be the easiest and the shortest one to use. And so we are going to use that method. For double integration method, we will start with the equation d square y by dx square is equal to moment about any section x divided by the bending rigidity EI. So the governing equation here we get is d square y by dx square is equal to, the moment becomes force F into x, it's a clockwise moment and we have taken anti-clockwise positive. So d square y by dx square is equal to, the moment that this force creates is F into x, it's a clockwise moment and we take anti-clockwise positive, so clockwise will be negative. So we have minus F into x divided by EI. So this is the governing equation, d square y by dx square is equal to minus fx by EI. In order to get the slope, we will integrate this equation once. So theta, that is the slope, dy by dx is equal to, by integrating on the right hand side we get minus f, integration of x is x square by 2EI. Because f, e and I are all constant values, plus the constant of integration c. Now in order to obtain this constant of integration, we'll use the boundary conditions. Let's write the boundary conditions here. At x equal to L, we have a fixed support. At x equal to L, there is a fixed support, so slope is 0. Hence we can write theta at O is equal to 0. So if we put this boundary condition in this equation, we'll have the value of C. Hence theta is 0 is equal to, we have minus f, x is put as L, so L square by 2EI plus C. By solving this, we get C is equal to FL square by 2EI. Let's put the value of C here and write the governing equation. So we'll have theta is equal to, positive term first, FL square by 2EI minus fx square by 2EI. Over here we can take f by 2EI common, f by 2EI into L square minus x square. Now we have such an equation where we can put any value of x to obtain corresponding value of slope at that section. We are being asked to find out slope at point Q, and point Q is at x equal to 80 mm. So along with the values of f, e, I and L, we can put x as 80 mm in order to get the slope value there. Let's do that. We have theta is equal to, f is 2 kilonewton, so we'll convert it to Newton, 2 into 10 to the power 3 Newton divided by 2 into E was given in gigapascal, we converted it to Newton per meter square, and it was 210 into 10 to the power 9 into I we already calculated, A raised to 4 by 12. A is 6 mm. Let's convert it to meter. 6 into 10 to the power minus 3 meters raised to 4. Numerator raised to 4 divided by 12. You have to be careful while putting all these values. What value is raised to which power should be carefully written. So this is our constant value into L is 100 mm. We'll convert that also to meters. So we have 100 mm as 0.1 meters, square of it, minus 80 mm is 0.08 meters, square of it. Let's put this in the digital calculator to calculate it. We have theta as, this becomes 2 getting cancelled. For the order of 10, we get 10 to the power 9 into 10 to the power minus 12, that is 10 to the power minus 3, goes up, becomes into 10 to the power 6. And here we have 1 divided by 22,680 into, this bracket evaluates to 3.6 into 10 to the power minus 3. So we have theta as, when we calculate for all this, we get it 0.1587. All the values are uniformly substituted in their corresponding SI units. This value that we get is directly in radians. So the slope at point Q is 0.1587 radians. Slope at point Q. Let's write the answer. We have magnitude of slope at Q, 20 mm from fixed end is 0.1587 radians. To learn more about deflection of beams, you can refer to the NPTEL video Lecture 30, Deflection of Beams 1 from the course lecture series on Strength of Materials by Professor S. K. Bhattacharya. He is from Department of Civil Engineering, IIT Kharagpur. I hope this solution will help you clear your doubt. Thank you.